Ready to go. All right. I've got a couple of reminders for myself. One is to provide you with a formula sheet for gravity, and another one is to homework for turn-in spot. That's the one I handed you out on paper last week and said it'd be due tomorrow. And I'm going to make it due at 11:59 p.m. So basically, don't stay up too late, but anyway, you'll be able to do that. So today we're starting optics and the study of how electromagnetic radiation interacts with things, and we'll be mostly concerned with visible light, so in this section at least. And some things about light. We use the lowercase c to stand for the speed of light, and it is this, and that's a 2 starting there. And for approximation purposes, most of the time we're just going to use 3.00 times 10 to the 8th meters per second. Way back in 1983, I had started subscribing to a magazine called Physics Today when I joined the American Physical Society at that time as a student member. And the August issue always had a table of fundamental constants of physics in it. And when I got the August issue that year, it had this notation or this in there. And I saw that it was exact. And I thought, what? What in the world? How could they possibly do that? And it turns out a few years before that, it had become, actually several years before that, it had become possible to measure the speed of light more precisely than they could measure the distance between two scratches on a platinum bar kept at a particular temperature in a museum in France. And so at that time, they realized that platinum bar wasn't such a good thing anymore. And here's the problem. If you've got a couple of what you think of as nice little scratches in there, maybe you made them triangular shape or something like that. If you look at this thing under an electron microscope, the sides of the V as you're going down are kind of bumpy, as is the bottom of the V. And so that's what it might look like. Now, you'd have to magnify it way up to have that be the case, but what are you going to define as the bottom of the V? So that's the problem with using something like that, the distance between two scratches on a bar, to say what a meter is. And so they just decided we are going to define the speed of light to be this, and a meter, they had a different definition for the second. It's a vibration, a certain number of certain wavelength or a certain mode of vibration for a cesium atom. And it was carefully defined in terms of which isotope of cesium it was and everything else. And that was how the second was defined. So they just defined the meter or the speed of light to be this number. And a meter is then 1 meter is equal to 1 over 299,792 458 of the distance light travels in 1 second. So nice, tidy definition, and that's why the speed of light is exact, because it's defined to be this number. So the meter is now defined in terms of that. So anyway, that's something about light. All right, we'll be doing some introductory material today, and then we'll have our light unit is actually 2 sections, but we'll have 1 test on it. Anyway, section 1 is what we call geometric objects. optics. And for geometric optics, we'll deal with things like lenses and mirrors and refraction, things that happen as light goes from one surface to another, and image formation and things like that. And for the geometric optics, we have to have that the wavelength of light that we're using is much smaller than any physical dimensions of the system. And so when we talk about lenses, we'll have things that are, maybe 38 millimeters in diameter or something like that. Section 2 for light is called physical optics. And we'll be looking at things that happen when the wavelength of the light is about equal to the dimensions of the system or smaller, or maybe I should say less than or about equal to the dimensions of the system. And physical optics will have things like interference going on. And so we'll think of light from two different sources, sometimes two narrow slits in something, and look at the interference. In that case, we'll also have diffraction, which is a spreading out of a wave as the wave goes through a narrow opening. And I'll try to show you demonstrations for as many of these things as I can. Some of them I've recorded videos of. Let's see. Hopefully I still have those things around, but some of them we'll be able to demonstrate during our lab periods and things like that. So it won't be too mysterious. Anyway, we'll have two separate homework assignments on this, one on geometric optics and one on physical optics. And each chunk will last a bit over a week. So that's how we'll sort of spread out the material on this stuff. Okay, a couple of really basic ideas. And here's one of them. Something we're going to talk about in a lot of what we do with light. And that is that this might be some sort of a surface, and it could be a reflective surface, something that light can go through, but we might also call it an interface between two different mediums. But let's suppose it's a reflective surface for starters. And we'll talk about, usually use the term a normal to the surface, and that's a line that is perpendicular to the surface. And so we're going to use that definition that we used before. And one of the first things that you are probably aware of, that when light comes in and hits a surface, something that we find out is that it'll reflect off of, and this could be, actually light reflects from all kinds of things, but if we measure the angle that incoming light makes with the normal, we'd call this angle theta sub I. That would be the angle of incidence. And then this angle over here would be theta sub R, the angle of reflection. And in this case, something that's pretty well known is that when light strikes a surface and bounces off, the angle of incidence is equal to the angle of reflection. And so that's one of the very basic ideas in optics. So nothing terribly surprising about that. This in a much higher level, or a higher level electricity and magnetism class, you might study this. And it turns out that the collisions that the light has with whatever it is they're bouncing off at this surface are elastic collisions. And so the light coming off there does something like this. If they were inelastic collisions, you could have that being different. But we don't have to worry about the details of that. We just remember angle of incidence equals angle of reflection. So that's part of it. Then let's suppose that the we've got another interface, and this time we're going to be interested in light that goes into the other medium. So here, this might be medium 1, and this could be medium 2. And we have light that's incoming here. And so this could be the angle of incidence. And we'd find out that if these two mediums have a different optical property from each other, the light will bend as it does this. And so you can have something like this going on, where in this case, we would say that the light is bending toward the normal. And this time, the theta here, actually, we might call this theta 1 instead of theta I, and we could this theta 2. But the angle bends toward the normal. Turns out if we went in the opposite direction, if we were in medium 2 and we had the light going up there, it would follow exactly the opposite path. And so there was a physicist, way back in the, I don't remember which hundreds it was, probably 1700s, but his last name was Snell. And we have something called Snell's law. And it's that one of the properties that we'll use to describe medium 1 is something called its index of refraction. And we just use a lowercase n for that with a subscript of whatever. We could use all sorts of different subscripts. But down here, we've got medium 2. It'll have that. But what we find out is that n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. Well, what the heck are those indices of refraction? Here are some properties of them. And another sheet of paper. Index of refraction properties. Well, one is that the speed of light in a material is equal to c divided by the index of refraction of that material. C, by the way, I didn't say this, is the speed of light in vacuum. Okay, so that's something that happens. Something else that happens is because V is going to equal F lambda. When a beam of light comes to the interface between two media, it'll have a particular frequency in one of the mediums. Well, that means a certain number of waves per second will arrive at that medium. Turns out the exact same number of waves per second leaves that thing. You don't have a bunch of waves building up and not going anywhere. They all pass through with the same frequency, but what changes is that the wavelength changes. And so you'll have C over N, whatever that happens to be. And what you end up with is that the wavelength, which is the speed divided by the frequency, and the frequency never changes. The speed does, though. You'll end up with C over N divided by the frequency, or you could, let's see, I guess you could write that as 1 over n times c over f. This would be the wavelength in vacuum, and so you could call that lambda naught, and this will be lambda naught over n is what it is. Lambda naught equals wavelength in vacuum. And so the wavelength in any other medium is going to be the vacuum wavelength divided by the index of refraction. Now, for a lot of what we do, we're not going to be concerned too much with the wavelength difference. But let's see, when we get to physical optics, one of the types of interference that we'll look at is something called thin film interference. And when we study that, we're going to have to take into account the fact that the wavelength will change when it's in a thin film of something. Sometimes that's used to our advantage. For instance, a lot of lens coatings you see on not necessarily cameras, but certainly on binoculars will be coated with materials to cut down on reflection so that you increase the transmission through the thing. So I don't know, lots of that's coming. But anyway, I want to show you some indices of refraction for different things. And got these up here. I don't know if you can see my cursor when I'm doing this, but got solids, got different indexes of refraction for them, or indices of refraction. Ice 1.309, fluorite, whatever that is. I think it's used in some lenses actually. Polystyrene, rock salt, all kinds of stuff. Quartz, SiO2. Okay, that's a mineral, and you can find it in certain rocks. Zircon, diamond. Diamond, if you look on here, it's actually got almost the highest index of refraction of anything on here. That's one of the properties of diamonds that makes them look nice as jewels, is their high index of refraction. You end up with a lot of reflections going on inside that. Fabulite, I'm not sure what that is. I don't know. Oh, this is, I don't know. I'm guessing you pronounce that rutile, but I'm not sure. It's titanium dioxide anyway, 2.62. It's actually got a higher index of refraction than diamond as well. Okay, different types of glasses. With those, they're all roughly the same thing, not a whole lot of difference. You can change the index of refraction a little by mixing stuff in. A lot of glass is actually silicon dioxide, or that's one of the primary ingredients, but you can mix other things into it. Flint, for instance, and you've got those things mixed in, and that'll give those things different indices of refraction. Borosilicate, which is Pyrex. Now, I guess nowadays, if you buy cookware that says it's Pyrex, it may not be the same borosilicate glass that it used to be. One of the advantages of the old Pyrex was that it didn't expand and contract as much when exposed to temperature changes, and so it was less likely to shatter, so it made good bakeware and stuff. But now a lot of the stuff they sell isn't borosilicate glass anymore, and so it doesn't have the same thermal properties. Anyway, various liquids, water 1.333. We'll use water as a medium for stuff to go into a lot of times, so that's just helpful to remember. Canola oil, corn oil, peanut oil. I'll show you a demonstration tomorrow with canola oil. It's kind of an interesting effect. Okay, and then gases. The only one I've got on the list here is air at 15 degrees Celsius. And something to notice here, it's 1.000277. Okay, what that means is light doesn't go much slower in air than it does in a vacuum. And so for an awful lot of the things we do, we're just going to treat air as if it's a vacuum and just say the speed of light there. Because to four significant figures, the light goes just as fast. And so we won't have to worry about the effects that it has, because most of the time we don't have that many significant figures. But anyway, there's a bunch of different indices of refraction, and they've probably got a table in the book with other ones as well. So that's the way that those things happen to work out. So let's try a few example problems here. Okay, what did I do with the first batch I printed off? Here they are. Okay. When the light in the figure passes through the glass block, it is shifted laterally by the distance d if n, that's the index of refraction of this glass block, is 1.50. Find the value of d. Okay, well, let's kind of blow this picture up a little bit, because that was something I couldn't do very well when I printed it off. And just expand our scale by a bit. So, whoops. We'll make this thing our 1.00 centimeters. And then try to see how this relates to here. And this is where we've got an index of refraction of n. Unless otherwise told, assume that the air, that what you have outside of here is air. So anyway, we're told that n is equal to 1.50. So let's figure out what happens at that first interface. Okay.
You're still on the index of refraction sheet.
Whoops. Okay. Got to get back. Thank you. All right. Where's my mouse pointer? All right. Back to this thing. Okay. I should know. There's the green outline around it. Okay. So here's the problem. We're told when the light in the figure passes through the glass block, it's shifted laterally by the distance d. And I'll zoom up the sketch that we've got here. So we have that. So anyway, there's light that comes in here and hits this glass block. This is glass here, and air here, and air here. So stuff comes in and hits the glass block, and the light ray makes a 32.1 degree angle with the normal here. Now, here's something, well, we'll study a bit about this anyway, but the light is going to bend here, and we'll see what happens inside this. And something I can say is that in air times the sine of 32.1 degrees is going to equal n for the glass, I'll call this n sub g, times the sine of, just call this theta sub g, okay, the angle that it makes in the glass. Well, in air is 1.000. Let's see, and then we finally start having other things. So I'll just treat that as 1.00 because that's about what it is. And so I don't have to worry about it. That means that the sine of theta in the glass is going to equal 1 over the index of refraction for the glass times the sine of 32.1 degrees, or theta sub g will equal the angle for which the sine is, that's the way I learned to deal with these things, times the sine of 32.1 degrees divided by index of refraction of the glass, which is 1.50. So I just plug that into my calculator and see what I get. Let's see. Whoops, I didn't want to do that. Clear sine to the -1 of, shoot. Oh, well, I'll have to, there we go. Nope, inverse sine. If these buttons, if you punch them a bunch of times, it toggles through the selections. First, I'm going to do the 1 divided by 1.50. Hadn't ever tried this calculation with this calculator before. And then I'll have the sine of 32.1 in there. And hopefully that's the right things. Anyway, I get that in the glass, I get 20.7 degrees. And so on my blown up diagram, which is over here, I've got 20.7 degrees. So let's continue on with our ray here now that we know that angle. Okay, and then I'll draw another normal to the surface here. Up here, and the light's going to come out of there. This angle will end up being theta sub g again, because these are parallel surfaces, and this line makes the same angle up there anyway. I forget, alternate interior angles, maybe. I don't remember what they are. But what comes out on this side, let's see, if I draw a line that's a continuation of the incident ray, that I'll have a ray coming out there. I guess I should continue that on, maybe. I'm not sure. Try to draw something like this. Here's the exiting ray, and I'd be back to 32.1 degrees over here, because what I would have at this interface is in glass, sine of 20.7 degrees is going to equal N for the air, which is 1 times the sine of theta sub air. That's the exact same equation that I had over at this interface. Over here, I was solving for the angle in the glass. Here, I've got the angle for the glass, and I've got that, and I'll just have the same angle in the air. So this will be 32.1 degrees again. And the question is to find out what that displacement D happens to be between the line of the incident ray and the line of the exiting ray. And what happened is it gets displaced there. So we've got that's the distance D that we happen to be after. Okay, well, knowing that this is 1.00 centimeters here, I can do a little bit of work to figure this stuff out. If this is 1.00 centimeters, this is the side opposite. So this will be 1 centimeter times the sine of 27 degrees. 27 or 20.7 degrees. And that's equal to Now this is just a little bit of trigonometry to mess with this. And I get about 0.353 centimeters. Okay, well, this distance, total distance here is going to equal 1 centimeter times the sine of 32.1 degrees. So which is 0.531 centimeters. So that's that total distance, which means this part right here, what should I call it? H, maybe? H will equal 0.531 centimeters minus 0.353 centimeters. Or 0.178. Okay, so that's how high that happens to be. Well, I've got another little right triangle here. If I can just figure out what these various angles here, well, if this is 32.1 degrees, this angle here is going to be 90 minus 32.1. That means this up here will have to be 32.1 degrees again. And that means actually D over H. Hope you can see that. D over H will equal that's H, not N, the cosine of 32.1 degrees. And so that displacement will end up being H, which is, where was it? 0.178 centimeters times the cosine of 32.1 degrees. And so the displacement of that thing ends up being, when we finally calculate it, let's see, 0.151, 0.151 centimeters, which is 1.51 millimeters. So not a lot of displacement, but that's just an example of using that Snell's law a couple of times to figure this out. So, okay, there's our first one. Here's a submarine problem. They're always fun. So let's see what we get out of that. It's 302 meters horizontally out from the shore and 107 meters beneath the surface of the water. A laser beam is sent from the sub so that it strikes the surface of the water at a point 209 meters from the shore. Okay, well, we better draw a picture. So we'll just imagine this is the shore, and here's water here, and we've got the source of the laser beam here, which is, well, that's not quite the scale. I better forget that one. This is 107 meters down. And the distance out here, and this is a really steep shore here, 302 meters over here. That looks approximately right. And this laser beam strikes 209 meters from the shore. So I'm going to just kind of guesstimate here that there's the direction of the laser beam. And this is 209 meters from the shore. So There's the normal to the surface at that point. And what's the question? If the beam just strikes the top of a building exactly at the water's edge, find the height of the building. Huh. Well, okay, so here's our building that's right at the shore of the water. And it's got a bunch of windows on it. These are not to scale, so those are great big windows. But anyway, this beam is supposed to just bear at the top of that thing. And I may not have chosen the right, I think I did though. I think I'm qualitatively correct. So this will be theta sub I, and this will be the refracted beam, theta sub R. And something I can say is that N for the water times the sine of theta sub I will equal N for the air times the sine of theta sub R. And what we're actually after is how high this thing is. Actually, we have to pretend that the building is down here too. So somehow the water is exactly like that. So, well, let's see what we have to do. One thing we don't know is this angle of incidence here, but it's the same as this angle here. And if this is 209 meters and this is 302 meters, and that's 107. Let's see, 309 minus, or 302 minus 209, that looks like 91 plus 2, that's 93 meters. And ignore the ripples in the water. Pretend it's just a straight line. So theta sub I is going to be the inverse tangent of 93 over 1 over 107. So it's just the number. The hard part on here was drawing the picture, I think. I get 41.0 degrees for that thing. Now I can apply Snell's law here. N for the air is 1. N for the water is 1.33. Maybe it's salt water, but we'll pretend it's in a lake. Actually, during World War II, the United States Navy did submarine exercises in Lake Ponderay, which is freshwater up there in northern Idaho. And so we can figure that out. Anyway, sine theta sub R. The N1 is understood here that it's 1. Is going to equal the index of refraction of the water times the sine of theta sub I, which we just figured out, 41.0 degrees. And so theta sub R will equal inverse sine of index of refraction of water is 1.33 sine, sine of 41.0 degrees. So here, that refracted angle there is going to equal, let's see, inverse sine of and that's 60.7 degrees. So that works out pretty good. All right, now, if that's 60.7 degrees, This angle here is going to be 90 minus 60.7, which is, it would be 30 degrees. It's going to be 29.3 degrees. So this angle plus this one equal 90 degrees. And now I've got a triangle where I've got the height of the building here, H. That would be the side opposite this angle. And it looks to me like H divided by 209 meters is the tangent of 29.3 degrees. So H over 209 meters is tangent of 29.3 degrees, or H is 209 meters times that. I'm gonna Okay, so pretty tall. I get H is 117 meters high. So this is I don't know, like a 10-story building right at the edge of the water. Okay, there's another nice little weird problem. Okay, this is a problem I've had on tests a few times. So try to understand what's going on here. In a physics lab, light with a wavelength of 632.8 nanometers in air travels from a laser to a photocell in 17.0 nanoseconds. Okay, so it's traveling in air when a rectangular slab of glass 0.796 meters thick, that's a thick slab of glass, that's 80 centimeters just about, is placed in the light beam with the beam perpendicular to the faces of the slab. It takes light 21.2 nanoseconds to travel from the laser to the photocell. What is the wavelength of the light in the glass? Hint, start by drawing a picture, then determining the laser to photocell distance. All right. By the way, this wavelength, 632.8 nanometers, is the wavelength of a helium neon laser, which is one that uses a gas of mixture of helium and neon to produce the light. And little tiny lasers that you like pen lasers and things like that aren't of that type. Anyway, they're usually a solid state laser of some kind. You can make them a lot smaller. So anyway, here's the laser and here's the photocell. And the light goes zipping along there. First thing we're going to do is figure out what this distance happens to be. And this distance will equal, well, what do we know? It takes 17.0 nanoseconds to get there. That's going to equal C times 17.0. Nano is 10 to the minus ninth seconds. And C is 3.00 times 10 to the eighth. So that distance between the laser and the photocell is going to be 3 times 10 to the eighth times 17 times 10 to the minus ninth. And I get 5.10 meters. Okay, now it doesn't matter where we stick this slab of glass. If we stick it here or over here or anywhere, it's going to have the same effect. So let's just take that slab of glass and stick it right here. So there we've got this thing. And this is 0.796 meters. Now, for the second part of the problem, it's going to travel in the glass for 0.796 meters for some amount of time that we'll figure out. And then it's going to be traveling in air the rest of the way at the regular speed of light. So we can figure out how long this takes. And once we know how long this takes, we can figure out how long it spends in that. So the distance in air for this is going to be 5.10 meters minus 0.796 meters. So we're going to lose a sig fig on the subtraction. We'll still have three significant figures, but we'll lose the precision of this thing. I get 4.30 meters there. The time in there, remember, this is going to be the speed of light times some time in the air. Okay, well, the time in the air is going to equal 4.30 meters divided by the speed of light, 3.00 times 10 to the 8th meters per second. And it might help to express this time in nanometers. We'll see. Anyway, divided by, and I would actually get 14.3 nanoseconds. Okay, but they told me that the light takes a total of 21.2 nanoseconds to travel from the laser to the photocell. So time in photocell, or time in slab, I mean, is going to be the difference between that 21.2 nanoseconds and the 14.3 nanoseconds. So which is 6.9. Okay. Well, so now I know how long it takes the light to travel this 0.796 meters. And so that will let me figure out the speed of light in the slab. Speed in the glass is 0.796 meters divided by 6.9 nanoseconds. And I'm going to be down to two significant figures here just because this was a subtraction process here, and I lose one, or can lose one when I do that. So and I get about 1.2 times 10 to the 8th meters per second. So whatever this stuff is, it's got a pretty high index of refraction, because this will equal C divided by N. Speed of light divided by that, which means the index of refraction is going to be C divided by that thing. So 3.00 times 10 to the 8th meters per second divided by 1.2 times 10 to the 8th meters per second. And I think that's 2.5. Actually, when I hang on to all the significant figures, well, yeah, 2.5, 2.6, somewhere around there. Which is a high index of refraction. That's higher than a diamond, or in the neighborhood of a diamond. So maybe this is just a 79.6 meter diamond. I don't think Big Bend has the bit for that to buy one of those things. Anyway, we're supposed to figure out the wavelength of the light in the glass. Well, the wavelength is going to be lambda naught divided by the index of refraction. So take the 632.8 nanometers and divide by 2.6 and see what we get. And I get about 240 nanometers, two significant figures. Now, this is visible light. It's in the red part of the spectrum. This is down in the ultraviolet part of the spectrum. By the way, visible light has wavelengths between about 400 nanometers and 700 nanometers. So that's what we have here. Okay. The first batch of problems. Now, something that wanted to introduce to you today is something called total internal reflection. And we can actually, usually I have this done as an exercise in class, but I have light and air incident on a flat surface of glass, index of refraction 1.55. Fill in the table for the value of the angle of refraction given the different values for the angle of incidence. Okay, well, what we're going to have is in air, which is 1, sine theta air is going to equal in glass sine theta glass. And we're going to figure out theta glass. So since this thing is 1, I'll have that theta glass is going to equal the inverse sine, and I'm doing a few algebra steps at once here, of 1 over n sub g times the sine of theta air. So I'm going to punch this thing into my calculator once, and I'll just change the value of theta air from 5 to 10 to 20 to 30 to 45 to 60, just to see what's going on here. And being lazy here, first I'm going to have the 1 over 1.55. And I have to do that because of the way my calculator behaved when I tried to do the other thing. And sine of theta sub air, I'm going to write them all as 5.00. Then I can change them better. Okay, for that first one, I would get the angle of refraction is 3.22 degrees. So then I just go up here, visit my formula, enter. 10.0 should work. And I get 6.43 for this one. Do the same thing, go to 20. You just have to change that one number. And I get 12.7 degrees. And just keeping through here. If you see me go through here, let's see. I'll do that again. Whoop, dog's getting yelled at. We got a puppy a couple of weeks ago, and it's been quite the process. Anyway, now I get 18.8 degrees. Next, I go to 45. I'm big on figuring out ways to cut down on work. Okay, 27.1 degrees, and at 60 degrees, we'll see what we get. Actually 34.0. So there. Now, something you notice, this angle is smaller than that one. This one's smaller than that one. This one's smaller than that one. Smaller than that one. The bottom ones are always smaller. So something we could say here is fill in the blank in the following sentence. When light travels from a medium with a low index of refraction to a medium with a higher index of refraction, it bends. Well, all of these angles are angles measured with respect to the normal. And since these are all smaller, it's bending toward the normal. Okay. And so anytime you've got light coming in and it's traveling initially in a low index of refraction going to a high index of refraction, it's going to bend toward the normal. Now, how much it bends depends on the two indices of refraction, but as long as you're going from a low to a high, it's going to bend toward the normal. So that'll be the case. Now, let's see what happens when you go in the opposite direction. Light traveling in the same glass meets a flat interface between the glass and the surrounding air. The angle between the light and a normal to the surface is 10.0 degrees. What angle does it make once it's in the air? So now we'll have in glass, sine theta glass is going to equal in air, sine theta air. Now, again, the index of refraction of air is 1. And so I can solve for sine theta air or theta air. Theta air, sine theta air is just going to equal that. Theta air is going to equal the inverse sine of in glass sine theta glass. So we've got a 10-degree angle here. Let's see what it happens to be. Now, remember, this particular glass had an index of refraction of, I forget how much. Where did I put that problem? Here it is. 1.55. So actually, that shouldn't have been rocket science to figure that out or to find that. But I'll have, I want the inverse sine of 1.55 times the sine of 10.0. I think if I write it as 10.00, I can do this with a minimum of work. Okay, and I get, for 10 degrees, I get 15.6 degrees. So it came in, if this is I'll draw the light coming in from above. This is the glass. This is air again. And it comes in at a 10.0 degree angle, but it exits at a 15.6 degree angle. And so it's bending away from the normal. So okay, then let's fill in the table below and see what happens. So next I'm going to do 5 degrees. So let's see. Now that should be 5 degrees. 5 degrees, it was 7.76 degrees. 20 degrees, I'll have to do something with my insert button. .0, that should work. I get 32 degrees. Or 30 degrees. I get 50.8 degrees. Okay, next, 45 degrees. Domain error. What happened? Okay, well, notice these angles are getting bigger and bigger as I go in here. Maybe I could do it for 40 degrees. Well, clear. I'm going to go up here and replace that 45 with a 40. We'll see what happens here. Yeah, at 40 degrees, if I'd had that, I would get 85 degrees. And so that's getting pretty close to 90 degrees. Well, at some point it is going to be 90 degrees. And that means beyond that, it's not going to exit. And we have something happening called total internal reflection beyond a certain point. And that's what we're investigating right here. So let's go ahead and do a calculation about total internal reflection. There's an effect or something called the critical angle. And what it is that you're going from high to low. And here's the normal. And at some point that we're going to define to be theta sub c, what we'll have is that n high times sine of theta c is going to equal n low times 1, because you're going to have a 90-degree angle out here with the normal. And if you go beyond that theta sub c, well, at that theta sub c, no light gets into the low index of refraction medium. It just all reflects off. And beyond that angle, that continues to happen. So you can figure out what this is going to be. Theta c will equal n low, sine of theta c will equal n low over n high. And theta c is going to equal the inverse sine of n low over N high. And we just investigated where the N low happened to be air. If you're going from some medium into air, like glass, if N low equals 1, this theta C is just going to be the inverse sine of 1 over N high. Whoops, N high. And so that's something that we'll investigate a bit more tomorrow. But this effect is actually used in an awful lot of things. In fact, in binoculars, there are a couple of prisms that take advantage of total internal reflection. I'll kind of show you the setup on it. If you've got the barrel of a binocular that looks like this is just one of the barrels of it, and it's got a lens there, but it'll have a prism in the back here that is arranged like this, and the incoming light will hit the prism here and undergo total internal reflection, and it'll bounce the light over in this direction. And then you've got another prism here. And, oh, wait, nope, that's not quite right. I think it's more like straight there, but then it hits another prism here, something like that. Anyway, it bounces the light a couple of times and comes over here. And the reason that you want to do this, I need to check on my drawing of this. But anyway, it bounces it a couple times in here and with total internal reflection, and it has the effect of moving the beam of light over. Well, where you might want to do that is if you've got a couple of binocular barrels with great big lenses on them, the two lenses have to be farther apart than the distance between pupils on the eye for the average person. So you want to move those beams of light over. And they also have the effect of making the image that comes out be upright and correct left-right without being inverted too. So that serves a dual purpose. But anyway, used to good advantage there. Okay, I'm going to stop there. And tomorrow we'll do a little bit more with this and then start looking at some image formation. But I've got a poll up for when we might have a review session this evening, a when to meet poll, and I put it in the announcement today. So you might take a look at that. And I picked a fair span of time, and I'm hoping as many people as possible can make it to that thing. And otherwise, I'll record that meeting and put it up so you can see whatever goes on during that. And if you can't make it, but you have questions for review on optics, send me a message and I'll address whatever your question happens to be. Also, if you have any questions on the homework assignment and are kind of wondering about that, because I know a couple of the problems on there are kind of tricky. So we'll do that, and I'll stop the recording here, stop the share first, back to there, and end the meeting.